It's my honor and pleasure to introduce Suzanne Donovan. And Suzanne Donovan is the Director of the Strategic Education Research Partnership, the acronym which is SIRP, at the National Research Council of the National Academies. That's one of our parent institutions with the NSRC. In that role, she is directing the effort to create a new independent education research and development institution. She was the primary author and co-editor of 2 SIRP reports. Strategic Education Research Partnership proposed the design and governance structure of a large-scale research and development enterprise anchored by a compact of state governments. Learning and Instruction, a SIRP research agenda, details an illustrative research and development agenda directly tied to classroom practice. And you can learn more about this on the website, which is an important new initiative that the Academy is launching. I came really to know Suzanne by what we would say is one of the most popular and seminal reports that the Center for Education, which is part of, I hope I don't make this too complex, but there's a division of behavioral and social sciences in education. In that division, there's a Center for Education that produces hundreds of reports, but there's one that was released recently that has been absolutely the centerpiece, I know, of our work, and that is the book called How People Learn. There's also an abridged version or abbreviated version of it called Bridging Research and Practice that has become somewhat of a primer or Bible, I know, in our work. So you have in your packet additional information about Suzanne, and we are really thrilled and honored that she's been willing to come spend the morning with us and share the most cutting-edge current research about how people learn. Suzanne?
Thank you. It's an honor for me to be here in this absolutely gorgeous room, talking to a group of people who are in part responsible for the exhibits and fabulous educational opportunities that I've experienced over the last 20 years that I've been in Washington, and that my daughter, who's now 14, has made extensive use of time and time again. So I'm very grateful for the work that all of you do. The work that I'm going to be talking about today began with the first How People Learn book, which, if you know much about the Academies, the way we work is to pull together groups of experts from a variety of disciplines to come to an understanding of what the various fields have to say about a topic at hand. And in this case, the Department of Education wanted to know what various disciplines related to human learning had to say about how people learn. Before that book was even complete, and it included the contributions of people whose work ranged from studying infants and early learning processes to studying artificial intelligence, adult learning, neuroscience. Before that book was even complete, the department got wind of what was coming and said, well, what we really need is a second volume, which says what in all of this wealth of knowledge is relevant for education, and they were specifically interested in K-12 education. And what would we need to do, what research would we need to fund to actually make this useful to teaching and learning? And that second book, called Bridging Research and Practice, highlighted a set of key principles, which I'll talk about today. But one of the things we said in that second volume was that if you really want this to be useful to practice, you need to move from the level of general principles to specific examples that deal with cases that teachers confront in classrooms, the specifics of what do these principles mean if you're teaching about light or about exploration and discovery, or whatever your topic is, how do these principles apply? So the department funded a third book, and that's about to be released later this fall, called How People Learn, or How Students Learn History, Math, and Science in the Classroom. Making that link, which is really your job, between general principles and then designing instructional experiences is a major challenge, not a simple one by any means. As we began that work, I was listening to a set of lectures on tape that Richard Feynman gave. Feynman, for those of you who don't know, was a Nobel laureate in physics and was very well known as a brilliant teacher. He did an introductory set of lectures at UCLA in 1960, and these were recorded and remastered, and you can now listen to them on your drive to work in the morning. In one of his early lectures, he gives the big picture of what is this about. And he explains to his students, he says, imagine a man walking on a beach. He observes the sand, the rocks, the moon. He sees the waves, hears their sounds, notices the color, feels the heat from the sun. He knows there are living things in the sea. So there's death, there's hunger, and maybe in the man there's even thought and perhaps happiness. The complexity, anywhere we look, is always this great, and curiosity demands that we try to understand this complexity by searching for clues that simplify. Are the rocks and the cliffs like the moon? How is the sand related to the rock? Are the waves of sound like the waves of the water? He says we can imagine this great complicated array of moving things which constitutes the world is something like a great chess game being played by the gods, and we're observers of the game. We do not know the rules of the game. All we are allowed to do is watch the playing. Of course, if we watch long enough, we may eventually catch on to a few of the rules. The rules of the game are what Feynman said are fundamental physics. And the analogy I'd like to draw here is to the rules of the game of learning, what is now an emerging science of learning. All we are able to do is observe and guess at the rules, and then we use science to test our guesses. But critically, Feynman says, even if we knew every rule, and in physics, he said we know we don't, so much more the case in the science of learning, which is still a very young science. But even if we knew every rule, we may not know what move will be made next in the game, simply because the world is too complex and our minds are too limited. So with the learning game, not only is the learning game too complex for us to know how to design the best game given the rules, but we know that there are many rules that we don't yet have a hint about. For example, there are the whole area of the connection between cognition and emotion is an emerging area of research that's very interesting. But some of the key ideas in the science of learning were isolated by looking at cognition separate from emotion. So we know that as we move forward and link these fields, we'll come up with new understandings. But the How People Learn work was about looking at work already done and isolating some of those fundamental principles of how people learn. The three principles that we highlight are encapsulated very effectively in a children's story. Oh, there was your picture of Richard Feynman that was supposed to be up there, but given that there's all this light, you can't see it very well. The children's story is by Leo Leone, and it's called Fish's Fish. And this is a story about a little fish and a tadpole who are friends. And as they mature, the tadpole grows legs, becomes a frog, and can go out on land. And the fish says, well, come back and explain to me what you see. And so the frog comes back and says, you wouldn't believe what's out there. There are these fabulous things called birds, and they have beautiful feathers and wings. They have tails, they come in many colors. And as he's describing the bird, the fish imagines, you can't see it as well as I had hoped, but the fish imagines a fish with the accoutrements of a bird. Well, he goes on to explain what a cow looks like, and the cow, of course, has horns and an udder, generally has spots, and after the description of the cow, we get the fish that looks like a cow, and then finally, as you can imagine, he explains what humans look like. They walk upright, they wear clothing, they're of different sizes, and we get the fish's image of humans. Now, the point is masterfully made that our new understandings are constructed on a foundation of existing understandings. And of course, because the fish doesn't understand the significance of these features, he leaps out of the water wanting to see the world for himself and has to be saved by the frog. This is about student conceptions, about the conceptions of any learner. Many of you have adults coming into your museums, and it doesn't matter if the learner is a student, which we tend to focus on in our work, or an adult. The conceptions students bring tend to be very resilient. They are the foundation on which new knowledge is built. That's what Sally's presentation this morning was about. I'll try to move quickly through some other examples. Pancake Earth. When young children were given a lesson on the shape of the Earth being round, researchers interviewed them afterwards to see how they understood this. And they could repeat that, yes, indeed, the Earth was round. But they would then imagine that it must be a pancake, because that's a round shape on which you can walk and you don't fall off. The idea is that the constructed knowledge and research on babies produces evidence on how early this process of constructing an understanding of the world begins, long before children have language. We can study now the amount of attention they pay, the kicking and waving of arms that indicates fairly reliably where a baby's attention is. And so we now understand that that process of constructing an understanding of the world begins in the first days of life. By the time a child arrives at school, they've already got lots of models of how the world works. So this idea that we can teach them that the Earth is round has to somehow jibe with their understanding that if they stand on a ball, that's their experience of round. They fall off. Another example, the course of the seasons. Middle school and high school students are taught that the reason we have seasons is because the Earth is at a tilt on its axis. So it's the tilt of the Earth, not the distance from the sun, that creates the seasons. Despite, that example is another one from the Harvard-Smithsonian research project. Despite the fact that students seem to test accurately on that information, give them a few months and they'll go back to saying that the reason we have seasons is the distance of the Earth from the sun, because we have repeated experiences of things getting hotter as we move closer to a heat source. It's very hard to change that conception. Finally, there's the Dinah Turtles example, and this is one that's engaging in part because it deals with students who were physics students at MIT, and they were given this challenge. This is work by Andre de Sessa. They were given a computer screen with a Dinah turtle, an electronic turtle that moves across the screen, and they were given the challenge to hit a fixed target with the turtle by applying a force, but to do it so that the target is hit with minimum speed at impact. So anybody that knows any physics knows that if you want minimum speed at impact, what you want to do is hit early and light. You already have momentum in this moving turtle. All you want to do is shift direction. Well, this research was done with middle school children. And what did they do? Well, they allowed the turtle to move just below the target, applied the force, and then, of course, they missed. They hadn't taken into account that there was momentum. They're using the experience we have of throwing darts at a dartboard, or of having a still ball that we kick in a direction. So they wanted the closest and most direct line to the target. They didn't take into account momentum. Well, de Sessa also did this with some MIT students. They were physics majors, so they had already completed high school physics. So what did they do? exactly the same thing is the point. My slides are getting a little ahead of me. But those students did exactly the same thing. And when DeSessa took a student aside and interviewed her, she could reproduce the laws of momentum precisely. She would have gotten an A on a test. She just didn't apply them when she was working in this simulated environment. That and the examples we saw this morning are very strong evidence that has come initially from science. Science is where we were first sort of had it put in our faces how ineffectively learning experiences changed conceptual understanding. But work has been done since then in a variety of other fields. In mathematics, for example, there's a dominance of whole number reasoning. Generally, we're successful at teaching children early math, whole number mathematics, because most of our experiences in the world rely on whole number mathematics. But when we move to rational number, we begin to lose a great many students. The idea that 1/2 plus 1/3 equals, according to many students, the majority of students in 4th to 6th grade, 2/5, comes from using whole number reasoning and applying it to rational number. It's of concern that so many students in 4th and 6th grade think that, but in 8th grade, when students are already finished with rational number, moving on to algebra, 30% of students still believe that 1/2 plus 1/3 is 2/5. It's very difficult to get the shift from whole number reasoning to rational number or proportional number reasoning. That has many applications. 0.4 is believed to be a bigger number, a smaller number than 0.059 because 59 is bigger than 4. Multiplication always increases values is a problem when you're dealing with rational number, where when you multiply with something less than 1, it decreases the value. So that resilience of whole number reasoning causes a major problem for learning rational number. In history, and some of you work with history in the work that you do, there are also conceptions that interfere with the very understanding of what history is. For example, there's the everyday idea of telling the truth. Any child or any adult has frequent experiences of thinking about the truth as the opposite of a lie. Those are your choices. Either you tell the truth or you don't. Well, in history, we're constructing an understanding, and that understanding may be different if you're looking through one person's eyes rather than another's. If you're looking through a set of documents that had one purpose rather than a set of documents that had a different purpose. For students to understand that history is a construction of an understanding of the past, this everyday idea of there's a truth and then there's falsehood has to be given up, and that's proven to be a very resilient preconception that's hard to change. Students believe that the past is a deficit past, and those of you who work in history will be very familiar with this idea that as you present elements of the past, people today, not just young people but older people as well, think of the past as a less adequate version, a less sophisticated version of our more advanced status today. And if you think about it in our own lives, the experience of growing older generally means we learn more, we replace the things we have with other things when there are better versions of them. But to think of the past as a deficit compared to today masks that there may be changes in which one class advances at the cost of another, that we may have advances in some elements of life that have detriments for the environment, for example. So this idea that there can be change that is not in every way progress comes up against the resilient preconception that change is always a matter of progress, and therefore the past is a deficit. Also, change is an event. It's very hard for people to think of change not as something that was one way yesterday and then something happened and now things are different. In history, what we talk about are a change in a state of affairs, and it's very difficult for students to give up the idea of history as an event. And then there are more, those are sort of ideas about history in general, but there are more specific ideas, like the widely held belief that people in Columbus's day thought the world was flat. And Columbus, brave Columbus, went out in a flat earth world and didn't fall off the end. That was the discovery of a round earth. And the majority of students believe that story. Some approaches to teaching actually reinforce those very preconceptions that we know are problematic. In mathematics, for example, we often introduce the idea of rational number, of fractions, by looking at whole number examples. We look at a pie and divide it into parts. Each of those parts is more like a whole number, we have 4 or we have 3, than like a fraction, a percentage of one whole. When a student was asked, which is bigger, 2/3 or 3/4, and given these, oh, you can't see these, I'm sorry, there's too much light in the room. They're given pies divided into fourths or thirds, and when they're asked which is bigger, 2/3 or 3/4, one student answered, well, I guess they're about the same because they're both missing one piece. So it's that whole number reasoning that the very way we teach reinforces and conceals the fact that students need to go through a shift in how they think about the world, from whole number to proportional number. What do we do about this? This is where we move from what do we know to what do we do, the design experiences. In the How Students Learn work, there are some very ingenious strategies for dealing with conceptions. They generally fall into 3 categories. One is an example that I think is frequently used, I've seen it used in Smithsonian museums, where you create a discrepant event. An event in which students put on the table their thinking about something and then are confronted with the fact that it was wrong. The case of the dry ice was such an example. In one of the cases in the chapter on gravity, it turns out students think that air holds people to the earth. The pressure of air pushing down is what creates weight. They believe that gravity plays a role, that the mass of the earth plays a role, but they believe that the role of the air is actually very significant. So they're given a task early on. There's a weight attached to a scale, and they're asked, they know that the scale reading is 10 pounds. And then Minstrel puts a dome over the weight and the scale and pumps out the air, creating a vacuum, and asks the students, what do you think it will weigh now? The majority of students think it's going to weigh much less. So they get the experience of then weighing it and realizing they were wrong. Well, why do they have this idea? They have this idea because they see images of people in space who are weightless. And they attach to that image the idea that it's air that holds people down. So this kind of experience where they see for themselves that removing the air doesn't make the huge change in weight that they expected dislodges that conception. The flat earth idea, Bob Bain, who did a high school history chapter, after students discuss that idea, shows them this picture. Again, it's very hard for you to see. It's Atlas holding up the world. And the picture is dated to 150 to 73 BC. Most students have seen this image somewhere. And all of a sudden, they're confronted with the idea that someone in 150 BC thought the world was round. How is it that I believe everybody thought the world was flat in 1492? Another example that Bob Bain used was he asked his students how to imagine, to jot down some notes, imagining how Columbus's discovery of America was celebrated in 1592, 1692, 1718, 1992. So the students do that, and what they're trying to figure out is how you throw a party in each of those 100-year periods. Well, it turns out Bain then delivers a lecture that in 1592 and 1692, there were virtually no celebrations. Nobody thought that was a tremendously important thing to celebrate. Well, and by 1792, we have a new country, and the country is constructing an understanding of its past, and during that period, the importance of Columbus's discovery of America emerges. By 1892, it's in full swing, and you see major celebrations. In 1992, the Smithsonian celebrated the Columbian Exchange. It was no longer the Columbian Discovery. Columbus, Ohio, renamed Columbus Day to Indigenous Peoples Day. So students are now confronted with their own idea that 1492 was in everybody's mind the discovery of America, because the fact they had learned was that Columbus discovered America in 1492. With this discrepant event, well then how do you explain that there was no celebration in 1592? The idea that history is constructed is made more powerful by this discrepant event. So discrepant events are one very important way of dislodging conceptions. Other ways, strengthening recessive understandings. Most of the understandings that students have trouble grasping, there are other experiences in the world that are not as dominant, that suggest that there are weaknesses in the way they're thinking. For example, the dominance of whole number reasoning. Students have experiences working with sale prices. And even at fairly young ages, if a student wants something that costs $10 and it's on a 50% off sale, they know what the price is. So they are able to work with rational number, with proportion as a concept. They're able to calculate sales taxes. But that's not their dominant way of using number. If you can strengthen the recessive understanding, you can then balance against the dominant understanding more effectively. In history, change over time that's not prompted by an event is something students have experience with. In a class, you might, over the course of a year, come to trust a teacher. There's not a specific day on which you went or a specific event that defines the point at which you trust the teacher, but you may be able to understand that some kinds of change are not event-related. So strengthening recessive understandings is a second approach to working with conceptions. The last, and this is one that's also I've observed being used frequently in Smithsonian exhibits, is narrative accounts of this discovery of inventions. If you think about it, before we discovered any of the major discoveries, everybody thought the naive kinds of ideas. I mean, the fact that there was once an experiment measuring the weight of the dirt in which a plant was planted before and after it grew was an effort to deal with figuring out where does that come from. And before scientific work, before there was an invention, everybody tended to have the naive view. If you can take students back to that point of discovery, and if you can put them into the mindset of that age, how was it that this new knowledge was discovered? What did it change when it was discovered? You then have a route to getting into that preconception. They can change in the way that the scientists who made that discovery changed their ideas. One example of how to do that in the Genetics and Evolution chapter, the author, the curriculum designer, has the students actually read accounts by Paley, who believed that the world was created in a day by God, Lamarck, who believed that you see changes because as you use a certain feature, as a giraffe reaches for tall trees, its neck elongates, and Darwin, who believed in natural selection, that there was random variation among species, and that natural influences choose among variations in terms of promoting some and eliminating others. So students read each of those accounts, and then they're given examples, and they're asked to write from one of those perspectives. And they take turns. They use one and then the other. So most students believe some element of Lamarck. And in fact, you can see Lamarck in the newspaper. There was an article in the Washington Post where somebody was talking about reading research and saying that lots of people can't read because we've only been reading for a couple thousand years, and so we haven't had a chance for evolution to yet make us all good readers. Well, from a Lamarckian standpoint, if you read for long enough, you would become a good reader. But from a Darwinian standpoint, you need reading to be the thing that naturally selects you. You need to live longer and procreate more if you're a good reader. Now, is there any reason to believe that? Time itself will not create that outcome. So there are elements in that Lamarckian thinking that pervade society. It's still there, and if you watch for it, you'll see it frequently. So the idea is to get students to really think carefully about what those differences are. What would Lamarck have said? What would Darwin have said? And then how do you argue one over the other? So those are really the three ways in which these various chapters deal with the difficult preconceptions that students bring to work with narrative accounts, to strengthen recessive understandings, and to create discrepant events. The first principle, then, is that students' preconceptions must be engaged in the learning process for it to be effective, and you heard that in the film, that is a critical piece. Now, that being said, it is not alone enough. I mean, we know that you can create a discrepant event, and one discrepant event doesn't change the way students think. So let's go back to, we're going to go to principle 2 now, but let's go back to the story of the fish and the frog. If we think about it, everything the frog said to the fish was accurate and relevant. I mean, describing a bird as having wings and feathers and people as standing upright, those are all relevant and important characteristics of those species. So what's the problem? Well, the problem is they're surface features, and as surface features, they're not enough to create an understanding of the significance of those differences. There are no core concepts that anchor the surface information that's given. What would the core concepts be in the fish case? Well, adaptation. If the frog were able to explain to the fish the difference between warm-blooded and cold-blooded animals, then the information about feathers and clothing is no longer just the decorations on a fish, but it has a new kind of meaning. The purpose of those features becomes important or clear. The idea of mobility outside of water and the different challenges that that creates compared to mobility in the water is another core concept. We then understand wings and the upright posture as adaptive solutions to the challenges of mobility in a new medium. But those things were not explained by the frog. Now, where do we get the understanding of the importance of core concepts? The research on this is not actually fish is fish. There's a little more research than that. It began in the 1960s, and here what was the interesting idea was to isolate the differences between experts and novices. In many sciences, you see initial experiments that in their simplicity allow you to see something you couldn't see otherwise. Mendel's peas, for example, were ingenious in part because they were so simple. We could begin to see genetics because the example was so simple. The simple example here by Simon and Chase was to look at the differences between experts and novices in chess playing and to ask how we explain those differences. This is a game, well, it's difficult for you to see again, I'm sorry, but this is a chess game in progress. And what they did was get three groups, a group of experts, of world-class players, a group of masters, they're master Class A players and beginners. And they let them see this board for a few seconds, And then they took the board away, and they wanted them to place the pieces on the board as accurately as they could. Now, one hypothesis they had here was that experts remembered more. They had better memories. They were people who could store more information in their minds, and that explained their expertise. Well, it certainly looked that way in this experiment. With the first trial, the first few seconds, what you see what you would see if it weren't too bright in here is that the beginner players could only place about 4 pieces accurately on the chessboard. The Class A players could place 8, and the master players could place about 16. So that's huge differences in the number of pieces that were remembered. As you go through additional trials, you see each group can place more, but that initial difference is huge. It looks like the master players have much better memories. They then took this chessboard, and if you play chess, you'll know that the difference between this board and the previous board is that this is not a game in action. These pieces are randomly placed on the board. And then they asked people to do the same thing. This time, there was absolutely no difference. The master players could place the same number of pieces as the beginner players. This was a key. It's not a better memory per se. It's a better memory for specific things that have to do with the idea, the bigger idea of the chess strategy. Now, this notion that memory is chunked around ideas, in this case a chess strategy, has been tested in many different environments. For example, electrical engineers know how to look at a set of circuits and identify a whole group of circuits as an amplifier. Novices looking at that same set, every circuit looks the same. So you ask them to reproduce, and you get the electrical engineer able to reproduce a whole set of circuits as one idea, whereas the novice is looking at each circuit separately and can't reproduce many at all. So this is a consistent difference found in many fields, that there's a set of bigger ideas that organize knowledge. And what appears to be a difference in memory is a difference in the organization of knowledge that allows you to remember more details because they're part of a single bigger idea. So consistently we find that experts see patterns that novices miss. We see that novices categorize problems by surface features and experts by the major principle for solution. So, for example, when you have a set of problems in which there are springs and inclined planes, novices will typically look for problems that have the same surface features. So they put the spring problems together and the inclined plane problems together. Whereas experts will look at the solution, the principle used in solution, and categorized by that principle. So it's the conservation of energy that would group rather than the spring or the inclined plane. Experts' pause times are also different. When you give experts and novices problems, what you see is that experts generally take longer to make their first move. Novices will begin and repeat their moves on a regular, steady basis, whereas experts generally wait longer, and then you see them act much more quickly. The idea is that experts are identifying the pattern and deciding what is this a case of. When they know what it's a case of, they then can move very quickly. Novices, not knowing, will begin one thing, then another, and then another. We can think of it as trying to find something. If we have a very well-organized office and somebody asks us for something, we stop and think, where would I have put that? And then we know where to go and can move very quickly. If our office has absolutely no organization to it, all you can do is begin looking one place and then another and then another. So it really is the organization of the ideas in the mind, and Simon referred to this as indexing. It was the way that artificial intelligence really made a leap forward to understand that it was not just the information, it was the organization of the knowledge that was key. All of these rely on core concepts because it's the core concepts that are the organizing ideas. Understanding the core concepts are critical to the most difficult element of learning, which is transfer. You can teach somebody something that in that situation they learn, but when you move them to a new situation, transferring the understanding to a new situation is tremendously difficult. In this case, which you won't see at all, that's a target with an arrow. This was research done early in the century, in the 20th century, in which a target was placed under 12 inches of water. And there were two groups. This was an experiment in which one group was given a lecture on the refraction of light, and then the opportunity to try out throwing at a target underwater. A second group was given no lecture, but given the same amount of time practicing. The two groups performed equally well. When the target was moved to 4 inches underwater, however, you saw a big difference in the way the two groups performed. The group that had been given the lecture performed much better, having some knowledge of the refraction of light, the principle of the refraction of light. That, again, is research that's been repeated to determine the impact of understanding core concepts on the ability to transfer. Core concepts in rational number, that this was is more of a challenge because in math, people think of mathematics as involving manipulation of facts, of algorithms. And the idea that there are core concepts in mathematics comes as a surprise to some people. But in rational number, it's the idea that there is a new kind of number. It's defined multiplicatively rather than additively. It's a relative quantity and not an absolute quantity. If you can see here, what we have are two rectangles. The first, it has a side of 6 and one side of 6 centimeters, one side of 8 centimeters. Students are routinely give the answer when asked to fill in, when we have the larger rectangle of 12 centimeters, what the side number should be. And what do you think they say? Right, they say 10. They're looking for additive rather than proportional. So the core concept in rational number is a different kind of relationship in which we're talking about a multiplicative or relative quantity. If you know what the core concept is, and we were talking during the break, one of the interesting things about the How Students Learn work is we were working with a group of people who had spent years and sometimes decades working in curriculum development, who knew very well the content of their chapter. But when you said, what are the core ideas here? If we step back and say, when a student walks away, let's assume they're going to forget a lot of the detail of what they learned. What are the core ideas that you want them to take away that's going to help shape their thinking in the future? That was a very hard question, even for people with a great deal of expertise. So knowing what those core concepts are is critically difficult. And if you ask yourself that about your own work, what are the core ideas I want people to walk away with? It generally is more difficult for people than one would expect. But once you have that core idea, then the question is, how do you effectively work with existing understandings to introduce that core idea and to change existing preconceptions? In the case of rational number, Joan Moss did the rational number chapter, and what she found was that beginning with fractions is not helpful. If you begin with percents, because students have an understanding of percents, and there's some research that suggests that this is a privileged domain, we understand percents relatively easily, and the way we pick up language relatively easily. We can do halving and doubling, and we see this in babies. They already are attentive to halving and doubling in ways they're not attentive to other kinds of patterns. There's easy control of numbers between 1 and 100. So what Moss does is use visual images to convey this idea of proportional number, pipes, tubes, and beakers, where you can't break things into parts. You slide pipes over tubes and cover certain percentages, certain proportions of the tubes. So if we have the core idea, we can then begin to think about creating instructional experiences differently that bring that core idea to the surface and that deal with the kinds of conceptions that make the core idea difficult for students. Of course, in rational number, you then do have to go on to decimals and fractions, but students do better with fractions after they've had the concept of relative numbers solidly in place. Core concepts in evolution, I want to leave time for questions, so I'm going to move a little more quickly. Natural selection, we've already been through. So it's clear that the core concept of natural selection has to be there. The point, though, is that for a core concept to be absorbed, you need lots of exposure, and it needs to be in several different areas. One experience, we know, doesn't do it. You need repeated experiences. What's interesting at the new Koshland Museum is that they've taken just a few things that they've done in that museum, but with DNA, for example, they don't give you one example. They give you several different examples of working with DNA, with the idea being that one experience won't do it. You need multiple experiences for a concept to take root. Sometimes the core concepts are not just what the discipline would identify as core. Any biologist would say that natural selection is a core idea in evolution. But it turned out in teaching students didn't appreciate that there is a great deal of population variance out there. They tend to think there's actually very little. If you don't get that there's a lot of population variance, then evolution doesn't make sense. Natural selection doesn't have an engine. So one of the things that was done was students were given beakers and given sunflower seeds, and they had to sort the sunflower seeds into beakers by the number of stripes on the sunflower seeds. At the beginning of the exercise, they didn't really think there was any variation. Sunflower seeds were sunflower seeds. At the end, they see a natural distribution in which the number of stripes differs in sort of a bell curve. So it turns out that population variation is a core concept. And we know this because as students try to learn without that piece in place, they don't learn effectively. So the second principle, learning for understanding, requires both a deep foundation of factual knowledge. It's clear in all of the expert novice work that factual knowledge is not only, there is no expertise without detailed factual knowledge, but we need the understanding of facts and ideas in the context of a conceptual framework, and we need the knowledge organized for effective retrieval. So that's principle number 2. Principle number 3, I will move through as quickly as I can. We're back to the fish and the frog. If we think about, so far, we've given the frog a pretty bum rap as a teacher. I mean, he gave only surface features, didn't deal with the conceptions the fish had, but even the best constructed learning experiences are only effective if people are engaged in the thinking and learning process. If we think about it, the fish might have wondered what clothes would do to a fish, what an upright posture would mean for the ability to move through water. The fish could easily, by reflecting on his own background experience, could easily have asked a number of questions that would have made clear that the fish can't leap out of the water onto the land without there being major problems. But the fish was very passive in the learning process. The kind of engagement that presumably all of you go through as you listen, and people who are good learners in general, and it's true in the talk aloud protocols in expert novice research, are that experts are very good at what's called metacognitive strategies, monitoring their own thinking, asking whether they're understanding, and when they're not, what they need to know. Very good at questioning, very good at looking for the next piece of information. And that kind of monitoring, those metacognitive strategies, are critical to effective learning. They include things like predicting outcomes, explaining to oneself as you go, noting comprehension failures, and activating background knowledge. So all of those are metacognitive strategies that because they're an internal dialogue, they were for a very long time not part of the picture in research on teaching and learning. It's the dialogue we have inside our own heads. But work by Palancar and Brown sort of brought to the surface that this kind of dialogue tends to go on in the heads of students who are very good learners and not in the heads of students who are not good learners. But it can be taught. And the way that it's typically taught is to model it, to find ways in which the kind of questioning that we do as effective thinkers and learners can be encouraged in less effective thinkers and learners. So metacognitive strategies help students take control of their own learning. We found that they can be taught effectively, in part by modeling and giving students the opportunity to become the questioner, working in groups, things of that sort. They can be taught effectively in the context of subject matter. If you try to teach metacognitive skills separately, it doesn't work, they don't transfer. But when you're teaching a specific topic, you can teach metacognitive skills at the same time. And the findings have been in physics, written composition, mathematical problem solving, and reading comprehension. So there are a broad array of fields in which we've come to understand that this kind of metacognitive monitoring can be actively and effectively taught, and it makes a big difference in the learning and achievement of students. What are the strategies to support metacognition? I mean, I was thinking about this in terms of what you do in museum exhibits, and it strikes me as one of the most challenging things because you don't generally get the opportunity to engage students metacognitively, or you're not necessarily students, but people who come to your exhibits. On the other hand, people generally come because they are engaged, they're interested, and that's why they're there. You don't have the classroom problem where people are forced to be there, unless you have groups of students who are forced to be there by their teacher. But it still is a challenge to think about how you get metacognitive engagement of people, because no matter how good your exhibits are, if they're not asking questions, if they're not actively trying to think through things for themselves, it will go right by them. One example at the Koshland Museum, which I was at recently, and it's the only reason I keep using it as an example, predicting outcomes. There's an exhibit where there's an Einstein and a rodent and plant and a yeast, a couple of other things, and you're asked to choose what % of your DNA you think is the same as that organism's DNA. And the act of choosing, of predicting, means that you're actively engaging your own thinking process. So rather than show you, which eventually is done, they show you whether your answer is right or wrong and what the right answer is, you're engaged first in thinking about this for yourself before you're given the new information. So there can be ways in which exhibits can also engage metacognitive processes by encouraging the thinking before the teaching. Inquiry teaching is one way in science, but also in other fields like history, to do active problem solving, so that students, in the course of problem solving, we all are inevitably forced to engage in thinking. You can't solve a problem if you're not engaged in thinking. So inquiry teaching can be one key to metacognitive engagement. Reflective assessment. It's interesting. It turns out that something as simple as in a mathematics class, in an experiment, students were asked, one group of students were asked to solve a set of problems and then stop after each one and explain just to themselves why they did what they did. And another group of students were not asked to do that. The second group solved more problems. The first group transferred their learning more effectively. So on a new test, they performed better than the second group. The act of just thinking about why you do what you do turns out to be a powerful learning tool. So reflective assessment. Comparing solutions and group discussions are ways in education programs you can use them. It's harder in museum exhibits, but there are ways to get students to engage in the process of becoming the questioner and of having to answer so that when other students ask them questions, they can see the kinds of things they haven't thought about or haven't explained very well. So all of those are strategies for supporting metacognition. So basically, what we have in the How People Learn literature is some of the rules of the game, and I've laid out today 3. We know these aren't the only rules, and in fact, it's more comfortable to call them principles rather than rules. What we still need are further exploration of the rules. I mentioned that the whole area of the link between emotion and cognition is one very active area, but there are many others. And we need more strategies for playing effective games, and that's where you come in. Oftentimes, I mean, my own observation of museum exhibits is that often you see, even if people don't go in thinking about the rules of the learning game, you see some very effective demonstrations of having at least tacitly understood that knowledge, because there are some fabulous learning experiences that are out there in the museum world. So strategies for playing effective games is sort of a two-way street, where we learn more about how people learn by observing effective examples of that in practice, in the same way as we can use the principles of learning to inform how we create those strategies. So with that, I'll stop, and we have a few minutes for questions. Okay. I don't know that there was anything, I mean, the chess experiments were done to ask a variety of different questions. I don't recall that seeing the game up to that point was one of the things they experimented with. But they did, and for many areas of learning, chess is sort of a more simple context, because you're looking only for whether you understand how to win the game. For more complex problems like history, there's a lot more that comes into play for which that simple an experiment wouldn't answer the kinds of questions you have. But they did do experiments, for example, in which they allowed the chess experts to play part of the game and monitored whether they considered more moves and considered further ahead. So they were looking at both the breadth and the depth of their consideration. Did they consider more moves, and did they consider more likely responses to their moves? And the answer was no, surprisingly. They just considered different moves. Again, it's the understanding of the concepts and the set of potential strategies that determined which moves they considered. They didn't consider more overall. But I don't recall that there was anything of the sort you're asking about.
Do you mind if I go back here? There you are.
Thank you for your talk. It was quite interesting. One of the things I wanted to kind of draw out a little bit more from you was what our relationship may be to the visitor's prior knowledge. I was intrigued, for example, you took on the example of evolution and cited Paley, Lamarck, and Darwin, but didn't talk too much about Paley's point of view and sort of drawing the analogy, visitors who strongly believe in creationism. What is our relationship, potentially, to dealing with that visitor? Certainly the whole string of ideas that you put forward was to imply that we sort of disabuse them of perhaps wrong ideas that they bring about a subject matter. And I think many of our visitors, whether you're talking about something like evolution, and particularly in areas of history or other aspects of culture, have a very different point of view. They're not here to be disabused of an idea, but perhaps to see it reinforced, to give it some kind of credence or affirmation. So how do we deal with that sort of complex of feelings, attitudes about prior knowledge and what our relationship to it should be?
Well, it's an interesting question, and a good part of it has to be answered not by science, but by the decision about what the point of your work is. And if it is to bring, in the case of evolution, to bring scientific knowledge to people, then Paley's view, the creationist view, does not have a scientific basis. So disabusing of the observer of that as a scientific argument is something that I would think an exhibit would take on if your point was to convey science. And then the question is, how do you do that? If people hold that belief, how do you effectively challenge the part of it that is challenged by science? Whether there's a God and whether God had a hand in creating the world as it now is not something that science challenges or has anything to say about. But whether there is evidence that evolution has in fact taken place is something science has a great deal to say about. The National Academies did another set of, there's something called, Sally, you may know, it's Teaching and Learning About Evolution, which does a very nice job of drawing those lines. It's written for teachers, and it says basically you're going to have kids, and in your case you're going to have visitors who have the idea and who come to school with beliefs in their families that the world was created in 7 days to look the way it looks today, basically. What do I do with those? And it's a very nice effort to draw the lines between what's science and what is not, what needs to be challenged and what doesn't, and where the evidence is to support those different things. So if, on the other hand, your exhibit is about documenting cultural beliefs, then you would want all of those to be represented with the sort of legitimacy of being what some group believes. So it depends on the point of your exhibit.
This is just a comment. There's beginning to be considerable amount of work in people who are studying actually visitors to exhibitions that show that, unlike classrooms, visitors do an enormous amount of self-selection and pre-selection into exhibitions. So I assure you that the creationalist is not going to walk into an exhibition where in fact, some of that work was done at the Smithsonian, where from the door there would be a picture of a Darwin. And that's really, for me, one of the bigger problems in certainly informal learning and exhibitions, which is to attract, draw, pull the individuals so they don't self-select themselves out in that way.
Right. Right. Well, you know, one of the things I like about the Feynman analogy to a chess game is that the kind of game you want to play isn't determined by the rules of the game. It has a lot to do with who your opponent is. In this case, the people who are walking through your door. And one of the first things you want to know is who are they and how do they think? And if you're designing something that's going to be effective at reaching that group, then that's a different game you're playing than if your audience is different. So the design principle really has a lot more to do with the interactive features of those who come to the exhibits and the creators of the exhibits.
Excuse me. I think I need to be thinner.
Hello. I was just curious to know if some of the research looked at gender differences in utilizing or, developing the metacognitive strategies that you described.
There is quite a bit on gender differences in learning in general. I'm trying to think about whether specifically I know of anything on metacognitive strategies. And whether that's been done gender specifically. And I don't know offhand of anything that was done on metacognitive strategies by gender. The verbal skills in general tend to be learned much more quickly by girls than by boys, and in the sense that it has an aspect of that to it. You would expect but I don't know any specific research that separates by gender.
Time for a couple more questions? Oh, yes. I'd forgotten you, I'm sorry.
Hi, I have a question that has to do with metacognition. We're constantly trying to have exhibitions or programs that make visitors think critically and not necessarily believe what we are writing, but to question it. Now, how is thinking critically and metacognition? Like, I was thinking of the Columbus example that you gave, Columbus Day, how people celebrate it. If you would use the metacognition on that, the strategies that people would use is how, I mean, was there slavery there, slavery not now, and things like that. So thinking critically and metacognition, what is the connection between those two?
Well, I'm trying to understand your question. I mean, metacognition, it's helpful to think about it as discipline-specific in the sense that the questions you want to have going through your mind to be a good thinker in history, for example, are going to be different from the self-questioning you do in mathematics or in science. Actually, science and history have much more in common when you actually think it through than might at first blush seem. But in math, you're always asking, am I making progress towards a solution? You're not asking, whose perspective is this from? And in history, you always want to be asking, whose perspective is this from? So some of the internal dialogue is the critical thinking that's done in that specific discipline. But the case you're giving about slavery, that sort of gets at a more specific level. The metacognitive strategies are generally about taking whatever in history, asking what's the evidence for this, whose perspective is it from, why did whoever produced this form of evidence produce it, what was the purpose. So those are sort of considered the metacognitive questions. The more specific, what was the role of slavery here, is part of the engagement of the individual thinker that hasn't really been defined as a metacognitive strategy, but as a critical part of thinking.
You join me in thanking Suzanne.
Thank you. Thank you.
Two more things to do before we wrap up. The first thing is to kind of step back now from the day we've been together since 9 o'clock this morning. We don't take into account breakfast. And just to recap, you had the beginning experience where Judy and Arlene provided you with an opportunity to share what your education program was from the perspective of a postcard. And I think we stepped away from that and saw that there was a lot of differences in this room. And in fact, what was surprising to us is that there were many cards this group didn't pick that our experience in working with educators are more frequently picked than were picked here in this room. I then engaged you with the log and asked you if I planted a seed and the tree grew, where all that weight came from, and you had an opportunity to see a videotape produced by the Harvard-Smithsonian Astrophysical Observatory under the direction of Phil Sadler about, the challenges that we have with children's misconceptions and that tie from learning and obtaining those big ideas. And then you listened to current research from Suzanne. So I know I'm not going to give you a great deal of time to think, but I'm sure as you've been sitting here, you've been thinking metacognitively. I'd like, for those of you who are willing to do this, to share, when you walk out of this room, what are some of the takeaways that you've got out of today?